My name is Leily Kiani. I'm a postdoctoral researcher in the Fiber Technologies group at Lawrence Livermore. Since 2012, our group has been expanding our capabilities and expertise in fabrication of specialty optical fibers. We've recently developed a new fiber for telecommunications applications based on a unique fiber filtering scheme. This fiber could potentially double the information carrying capacity of optical fiber networks. There will be huge demand for increased bandwidth in the next few years. Internet traffic grows more than 20% every year, and mobile data traffic, which also depends on the optical fiber network, is expected to expand from 10 to 30 exabytes per month by year 2020. Right now, systems operate in the C-band and somewhat in the L-band. The C-band is fully saturated. Efforts now are focused on expanding the use of the L-band, but that too is trending towards saturation. Our technology enables a 100 nanometer band of use in the E-band. Historically, attenuation has been high in this region due to absorption by hydroxyl contaminant. But since the early 2000s, manufacturing improvements have lowered losses in this range to virtually their lower limit, enabling the full use of the band between 1300 and 1600 nanometers. But amplifiers of sufficient performance have not been made in this region. We have built such an amplifier, and we figured out how to do this in a form factor that is identical to conventional amplifiers. This is potentially a billion-dollar market. The C-band erbium fiber amplifiers were a $900 million market in 2012 and are projected to grow to $2.4 billion in 2019. A companion E-band fiber amplifier could eventually have a market comparable to that of C-band. The new amplifiers would be deployed in parallel with the existing amplifiers around the transmission fiber that makes up the backbone of the long-haul network. This would increase speeds and capacity while saving enormous costs by avoiding the need to dig holes in order to lay additional cable to accomplish the same effect. Conventional amplifiers are based on erbium. Ours is based on neodymium. Neodymium has an emission between 1320 and 1440 nanometers. Telecommunications researchers made several attempts in the 1990s to develop this application, but were unsuccessful. The main performance inhibitors here are gain competition, which is the tendency for neodymium to produce gain in bands that are not useful for this application, and excited state absorption, which is the tendency for useful gain to be reabsorbed. Our fiber addresses the issue of gain competition by suppressing undesired gain in other bands. In order to fabricate a new fiber, we start with in-house modeling techniques, and then we fabricate via the stack and drop process. We start with a highly pure glass rods and tube that are heated and gently pulled into intermediate elements that are approximately a millimeter in diameter. Those elements are stacked into a complex array that is uniformly drawn down to fiber dimensions. Our techniques allow us to take down the size of initial components by a factor of 1,000. Our design works by filtering away undesired light from the core of the fiber. The picture in the upper left shows a cross-section of our fiber. The dark regions are areas of lower index which serve to confine light in the core, and the bright regions form a wavelength-dependent path between the core and the outer ring of glass. These are made from graded index elements that are typically used to fabricate standard multi-mode fibers. So they're widely available and of high quality. In the bottom right, you can see that filtering region shown in black, and the gray curve shows the light that emerges from 7-meter length of pumped fiber. You can see that almost no light outside of the E-band emerges from this fiber, showing that we successfully suppressed the amplification of light in undesired bands. This is the aspect of this fiber that enables efficient amplification. This fiber was implemented in a benchtop demonstration by pumping 2 7-meter lengths with 4 over-the-shelf diodes. This amplifier demonstrated positive gain spanning the E-band region with a maximum of 13.3 dB. We also measured the noise figure to be between 5 and 10 dB in this range, and slightly above the theoretical noise figure due to excess loss. With some improvements, we believe we could attain the performance matched to existing amplifiers, that being gain above 30 dB and noise below 5 dB. In order to do this, we need to make 2 key improvements for better efficiency. We need to lower losses, and we need to increase the intensity of light in the core. We believe we've addressed the issue of lowering losses by using cleaner fabrication techniques. So we've reduced contaminants by washing components in a sequence of detergents, acids, and finally with a pure water rinse, and assembling the final preform in a Class 1000 clean room. In the plot, you can see that we can significantly lower the losses. The picture shown is a 70-meter length of erbium doped fiber made with these techniques, and you can see there are no bright spots, which are indicators of contaminant. Even though we have not applied this to a neodymium fiber, we believe that we've addressed the issue of lowering loss for a future fiber. Okay. Building a better fiber is the next step. But to operate in the E-band, complementary components will need to be made for amplifier integration and for the transmitter modules. These would be higher power pump diodes, gain flattening filters, and wavelength division multiplexers. Complementary components are expected to be straightforward extensions of existing technologies. The only substantial roadblock here was the development of an efficient E-band amplifying fiber, which we believe we've done. Okay. Lawrence Livermore can assist with amplifier development. We can transfer fiber and amplifier technology, and we'll license key IP. Thank you for listening. My name is Leily Kiani. If you'd like to know more, please contact Jay Dawson or David Dawes in the IPO office.